Hi everybody, hope you're doing good today. Now our next PowerPoint is going to be about carrying capacity. Carrying capacity is as simple as it sounds. How many organisms can the environment carry or sustain in a given area? And we're going to look at some numbers for a lot of different organisms and what's happening for them, including humans. First, let's get some definitions down. Some we've talked about already, but they're important for carrying capacity. So a population is a group of individuals of a single species that occupies the same general area. This is a new one, at least that we've never done. You might know this already. The exponential growth. Exponential growth is very fast, and it's because when populations can reproduce under ideal conditions. We'll get to more of that in just a little bit. Population limiting factors. Just like it sounds, it limits the number of organisms for that population. Hunting, the amount of space available for breeding, the amount of space for growth, the amount of space for food, and water availability, etc. We'll talk more about those later on. The logistic growth model, which is basically the logical growth model. This is what happens to growth because of limiting factors. And this is how population size slows down. Finally, carrying capacity, the maximum population size that the environment can support at a particular time with no degradation, easy for me to say, to the habitat. Meaning that the habitat stays the same. It doesn't get worse, it doesn't break down, there isn't any habitat loss, things like that. So that carrying capacity is a very, very important number, a maximum population that the environment can support. So let's look at exponential growth of bacteria. So if you get a single bacteria, and remember, bacteria reproduce asexually, so they're reproducing and making exact copies of themselves. Every 20 minutes, bacteria reproduce. So after 20 minutes, you'd have 2 bacteria. 40 minutes, you'd have 4 bacteria. First hour, you'd have 8 bacteria. Well, that doesn't sound like a lot. That's an hour. You only have 8 bacteria. Well, the next hour, you have 16. Next 20 minutes, you have 16. And then 20 minutes after that, you have 32. And after 2 hours, you have 64. Yay, bacteria, you have 64. Not a lot. However, if you take a look at the next 3, 4, 8, and 12 hours, let's see, this is hundreds of thousands, millions, that's trillions. You now have 68 trillion bacteria. No, billion. 100 billion. Billion bacteria, sorry. 68 billion bacteria. 20 minutes later, how many more are you going to have? That's right. You're going to double the population 20 minutes later. So you're going to have 1.2 trillion bacteria. Now, this is known as exponential growth, and you can see how that exponential growth curve gets after 120 minutes. It begins to go almost straight up. And eventually it would go straight up to the point where after 24 hours and one single bacteria growing under ideal conditions without any limiting factors, there would be a bacterial mat around the entire planet that was approximately 6 feet deep. Think about it. Bacteria mat all the way around the earth, 6 feet deep, all because of exponential growth. Now, luckily, there are limiting factors for those bacteria. And there's only so much space, there's only so much food, there's only so much water, etc., etc. So that limits the amount of bacteria that are able to grow. And that is what is known as carrying capacity. So eventually, if you were to think about the bacterial cells that were in this little beaker right here, they would grow exponentially until they reach the carrying capacity of this beaker. Then what would happen? That's right. This curve would go up and up and up and up and up until it couldn't go up anymore, and then it would begin to go down. Because now there's no more food. Now there's no more living space. Now there are those limiting factors that limit that population. So, logistical growth compared to exponential growth. Now here is our exponential growth. And here is our logistical growth, or our logical growth. And of course, this line is kept like this because of limiting factors. There's only so much space, there's only so much water, there's only so much food, there's only so many organisms that can be maintained by the environment. All right, so under ideal conditions, this is what the population does. Under real conditions, this is what happens. For a short period of time, the numbers of individuals do increase on an exponential growth scale, but then begin to level off to a much flatter scale. So if you take a look at the growth of a population of fur seals, so back in the 1910s, 1915s, a new set of breeding fur seals were added to some islands, and the populations were tracked. And for a period of time, they did have that pretty exponential growth line. It was pretty steep, but after it reached that 10,000 seal mark, you can see that some of those are up and down and up. This is the average that averages out because of those limiting factors. This logistical growth line flattens out the number of organisms that are able to survive and be healthy and reproduce to about 10,000 fur seals in those areas. So, what does the logistical growth model suggest about real populations? Is that population's growth rate will be small when there's a small population size, and it will also be small when there's a large population size. So it's small when there's a small population size because obviously there aren't many reproducing, but it's small that growth rate will be small when there's a large population size because of limiting factors and creating that carrying capacity. Limiting factors make the birth rate decrease and the death rate increase, or both, which keeps that population stable. Eventually the population stabilizes at carrying capacity where birth rates are somewhere equal to death rates. And that changes year to year. Sometimes you're going to have a good year where you're going to have more organisms that are able to be supported. Sometimes you have a bad year where the death rate is higher than the birth rate. These are mathematical models and no population fits perfectly. So, the sparrow population. Now you can see the sparrow population has a lot of ups and downs. This is mostly based upon winters. When there's a hard winter, that means not many sparrows are able to reproduce. That means their population numbers drop. Now when there's a small number of sparrows, it takes a little bit of time to get that population back up to what would be the carrying capacity. But when the environment changes and you have another bad winter 10 years later, 9 years later, those numbers, you can see very quickly drop off. Some populations remain very close to its carrying capacity. Most populations fluctuate, as you see over here. Boom and bust cycles. So you can see that predator and prey are going to be very closely linked to the food that's available. So you can see that in red we have the lynx, in black we have the snowshoe hare. And when the lynx population goes up, what happens to the snowshoe hare population? Exactly, it goes down. When the snowshoe hare population goes down, what happens to the lynx population? It goes down. When there's less lynx, then more hares can reproduce safely and survive, which means that the hare population goes up, and very soon after that, the lynx population follows. So those are the boom and bust cycles that they're talking about, and you can see that somewhere in here, if you were to draw a median line, that would be the carrying capacity for this area for that population of lynx and snowshoe hare. The hare cycles may be caused by increases of food shortages, during winterizing. It's what you do to cars or boats, Brandon. Winter cycles or overgrazing. Many of these fluctuations are due to predator-prey interactions as well, and the cycles are affected probably by both of those. Since predators reproduce more slowly than their prey, their population numbers always tend to lag behind the growth of their prey populations. And again, you can see that when the numbers increase for hares, soon thereafter, the numbers increase for lynx. When the snowshoe hare increases a lot, very shortly after, the lynx population increases a lot. You get the idea. Human growth. Well, let's look at it realistically. This isn't 6 billion anymore. It's now 7.5 billion people. The only actual decrease in the population that we've seen was in the plague. And you can see that for a very long time, when the human population was low, the growth didn't happen very quickly. But once we found modern medicine, whoops, try that again. Here we go. Once we hit modern medicine, we were able to extend the life of humans almost double what the normal lifespan was. The lifespan before modern medicine was about 45 to 50 years. Now the lifespan is about 75 to 80, depending on whether you're male or female. And you can see that currently we are on an exponential growth pattern. Will we be able to sustain this forever? No. There's only so much water. There's only so much food. There's only so much living space. And right now we are pressing other organisms and we are decreasing their population because we're taking their living space. We will eventually find the carrying capacity for humans on the planet. Right now, there's many populations that are finding those carrying capacities, and there are some places in the world where they go through hungry seasons, where their food is not available, and that is a major, major problem. There are estimates that the Earth can hold about 13 billion people. That's the carrying capacity of the Earth. There are other estimates that say that we are already at or above the actual carrying capacity of the Earth, because remember, carrying capacity also says that it's a population size that does not degrade the environment. Currently, we know we are degrading the environment. The issues that are going to be affecting those are overgrazing, losing of groundwater, rivers running dry because of water usage, etc. So, how to achieve stability? Well, it all comes down to birth rate and death rate. Zero population growth is when birth rates equal death rates. Pretty simple. There are two ways to reach zero ZPG. First, you can have high birth rates and high death rates, or you can have low birth rates and low death rates. Now, in most developed countries, we've seen that this zero population growth kind of takes care of itself. Because people live longer, because there's more societal help available through services, people have less children naturally, and so people usually only replace themselves or don't have any children at all, which leads to zero population growth. Let's take a look at what some more look like here. Oh, sorry, this is the doubling time for the human population first. So if we have annual rates of increase of 4% in our population, that means in 18 years, we will double the human population. That would be very bad. Luckily, our population growth is much lower than that. I don't know exactly what the number is. I think it's somewhere around 0.8 or 1%. I think it's more like the 0.5%. And we're slowly moving down. But doubling from 7.5 billion people to 15 billion people would be a serious problem even in 133 years. All right, the planet wouldn't be able to sustain that realistically. So our numbers are going to have to begin to flatten out to get to that logistical growth curve in order to have a safe environment. So what happens when you overshoot the carrying capacity? Well, there's a big what's known as correction. There's a large dieback that occurs that goes well below the carrying capacity, but then it comes back and you can see that it's always ups and downs. It doesn't just like level out at the carrying capacity and hold that level. Sometimes are better, sometimes are worse. Technology will help us to increase that population carrying capacity of the environment as we are able to manufacture foods, we're able to have them last longer, we lose less to waste, etc. So what does a stable population look like? We have the lag in the beginning where growth is small because population is small. Then we have our exponential growth. And then we have our state of equilibrium based upon those factors, limiting factors in place. And limiting factors are anything that prevent a population from growing any larger. They're very closely tied to carrying capacity. Disease, predators, available food, water, available habitat or habitat destruction of humans, poor reproductive success because of climate change, because of pressures from other organisms, hunting. All those are examples of limiting factors or overhunting. So a growth to stable population is logistical growth, and that is all caused by environmental resistance or those carrying capacities. And you can see those right here, that environmental resistance, disease, predators, limited living space, low oxygen supply, low food supply, keeping those carrying capacities at their levels currently. Now, if you take a look at the growth of human populations, you can see that United States has slow growth. Kenya has rapid growth, and Italy has zero or declining growth. That's because the people of reproductive age are not reproducing as many offspring as it takes to replace themselves. That means there are less available people in the population. That means Italy's will actually decrease their growth. Here you can see United States has slow growth. It is right there at that population right there, and you can see that as Kenya's under 15 population goes into its reproductive age, it will have children as well. Now the question is will they have as many children as the 15 to 44-year-olds are having right now, or will they begin to level out as well? That will all be affecting the growth of populations on the planet. So renewable resource management is also very important. We can't just take all the fish out of the ocean, because you can see what happens when we do that. The population collapses and they disappear. We have to manage those resources and only take out a certain number and a certain size of fish so that we can make sure that we get yield every single year. Maintaining that population properly will be the best for our food source, and also best for the cod as well. Finally, global climate change can affect populations as well, affecting the population of the lemmings and the fox. When things warm up, lemmings don't have a place to hide. That means foxes are able to get at them more easily. The lemmings die. The foxes don't have food. The foxes die. You get the idea.